My name is Prashant Shrestha, and today I'll be presenting the research project on hybrid optical radio frequency communication channel model. The goal of this project is to improve communication system by developing models that predict channel attenuation in hybrid RF or FSO systems, which focus on the impact of weather conditions such as rain, fog, and snow. The objective of the project is to develop channel attenuation models for hybrid RF or FSO communication systems. The system leverages radio frequency communication, which is reliable in adverse weather conditions, and free space optical with communication, which is FSO, which is which provides high bandwidth in clear weather. In this project, we focus on how weather conditions such as rain, fog, and snow, and so on, affect the signal quality in these hybrid systems. This work is important for applications in satellite communication, 5G backhaul, and disaster recovery. These hybrid systems can significantly enhance communication, especially in adverse weather conditions, by accurately predicting the attenuation caused by different weather conditions, which we can improve system with which we can improve system readability. This project involves analyzing real-world data on weather and communication signal strength to develop such predictive models. The dataset used in this project contains key weather metrics including rain intensity, visibility, temperature, humidity, and so on, which are the important features for predicting RF and FSO attenuation. The target variables for the models are RF attenuation, FSO attenuation. Additionally, the weather conditions are categorized using sign-up code, which includes weather types such as clear, rain, fog, and so on. And as you can see on the right side, there are like total 26 columns, out of which these two are the target variable, and that this is the sign-up code which represents the weather condition. And there are like 91,379 data rows of rows of data, sorry. And as you can see, it is a clean numerical data. The sign-up column in the dataset contains 7 unique values that represent various weather conditions. Each condition, each code correspond to different weather types that impact signal attenuation, such as rain, fog, or snow. This weather condition will be the key in modeling process. Here we can see that the distribution of weather condition in the dataset. Initially, the data was imbalanced with a certain weather condition overrepresented. We applied the data balancing to ensure that the models were trained with more even distribution of conditions, which helps to improve model accuracy. For modeling, we explore three approaches: specific models, generic model, and joint model. In the specific model, we train separate model for each individual weather conditions, and generic model, a single model will be trained across all weather conditions, and in the joint model, we will be training one model. We will be training a model where the prediction from one model is used as a feature to train another. In all these approaches, we will we use random forest for feature selection and model training. We identify key weather parameters like visibility for FSO attenuation and rain intensity for RF attenuation. Feature selection For feature selection, we for a specific model we selected features based on weather conditions that were most relevant for each model. As you can see, this is the feature selection for the uh, sign up code 7, which represents snow weather conditions. Here, the green line represents the uh, cutoff index from where like we won't use anything on the left side of the line. So all all the important features are on the right side of the graph. And among them, for the snow, temperature difference, rain intensity, hour of day are the most important uh, features for the prediction. Similarly, for the genetic model, we consider a broad range set of a broad set of data sets. We didn't take under consideration for any weather conditions. So like we just considered the sign code as any features like any other features. Here is also same like on all data sets on the left side of the green cutoff line will not be used for model training. Here we can see the architecture of method 2, the joint model approach. In this model, we will first predict the RF attenuation using using the data set, and then use the predicted RF attenuation as a feature to predict FSO attenuation. So for training this model, we will be using 70% of the data. For testing, we'll be using 30% of the data. So this allows us to improve the prediction of FSO by incorporating RF predictions. In method 3, the architecture is slightly modified. Here, first we'll be using our random forest model to make a prediction of FSO attenuation, and we will use that predicted FSO attenuation as a feature in our second random forest model to make a prediction of RFL attenuation. Similarly, we'll be using 70% of the data to train the model and 30% of the data to test the model. We evaluated the performance of all the models using two key metrics, RMSE, root mean square error, and R square, which is the coefficient of determination. RMSE measures how close the predicted values are to the actual values, while R square tells us how well the model explains the variance in the data. So we performed a comparison across all the models to assess their relative performance by taking average of RMSE and R square, or by choosing a model with worst RMSE score for worst case analysis. Uh, for this, I chose the former one, which is taking the average of RMSE and R square. First shows the RMSE comparison between the model across the various weather conditions, and we can see how well each model performs in terms of minimizing error in the predictions. So here we can see that the generic models tend to get uh, least RMSE error in most of the weather conditions, only where the exception is in the rain weather conditions. Except that, like most of the time, the generic seems to have like least RMSE, especially the RFL model. The R-square comparison plot, which shows how well each model fits to the data. A higher R-square indicates that the model explains a greater portion of the variability in the data. As you can see, the results are very coherent to the previous RMSE scores, where um, um, the generic model has greater R square value compared to the specific values, and one exceptions are like the in in the conditions like rain and snow, where uh, the generic model tends to have lowest R square values. After performing hyperparameter tuning, we observed that the generic model showed little to no improvement. This suggests that the hyperparameter tuning does not significantly affect the performance of the generic model, likely because it's already optimized for the given dataset, but for that, further analysis needs to be done. In this slide, we compare the best performing model with the joint model. And in our case, our best performing model is generic model. As you can see, both models perform similarly, where in but similarly, but the joint model showed slightly more higher RMSE error and slightly less R square, which makes our generic model a better choice. To conclude, we found that for generic model, rain intensity plays a major role in RF attenuations, whereas visibility is the most critical feature for FSO attenuations. The generic model marginally outperforms the specific model, whereas there was little to no improvement in generic model after hyperparameter tuning. The generic and joint model perform similarly, though the joint model slightly um, performed worse than the generic model. The future work will include the further analysis of future importance for predicted attenuations. It will include all the diagrams and all the analysis, and we will be further exploring entropy and information gain calculation for the model improvements. With this, I would like to end my presentation, and thank you for